These are the notes for 3-2 on linear functions. So a linear function has a constant rate of change. It fits the form y equals mx plus b, meaning it can be written as that in that form. And it has a power of 1. Another word for power is degree, and that just means the highest exponent. Okay, so functions are either linear or nonlinear. For them to be considered linear, it needs a constant rate of change. It can be expressed as y equals mx plus b, and it has a degree of 1. So a nonlinear function has a power other than 1. It does not have a constant rate of change, and the graph would not be a straight line. So depending on what representation you're given, whether it's a graph, a table of values, or an equation, would change your reasoning as to why it's linear or nonlinear. And then the graph of a linear function is the set of ordered pairs that form a line. So let's start by looking at these 3 graphs. We're going to determine if they're linear or nonlinear, and then why they're either linear or nonlinear. So number 1, this graph here, it's called a parabola. It is not a straight line, so this graph would not be linear. And the word linear actually has the word line in it. So that's one way to remember that for it to be linear, it needs to form a straight line. Number 2 does form a straight line, so it's considered linear. Number 3 also forms a straight line, so it is also linear for the same reason. Okay, so that's how we determine if a function is linear or nonlinear based on the graph. It's either a line or it's not. If we're given a table of values, it's considered linear if it has a constant rate of change. So if x is increasing by the same amount each consecutive x value, and if y is either increasing or decreasing by the same amount, then that would have a constant rate of change between each set of x and y values. So let's first look at the x values. Check to see how they're increasing or decreasing. Number 4, they're increasing by 3 each time for each consecutive x value. And the y values are decreasing by 6 each time. So this change is constant. X increases by 3, and the corresponding y values decrease by 6. So that is a constant rate of change, which makes it linear. For number 5, let's first look at the consecutive x values. 1 to 3, that's increasing by 2. 3 to 5, increasing by 2. 5 to 7, increasing by 2. The y values, 2 to 9, increasing by 7. 9 to 20, increasing by 11. And 20 to 35 increases by 15. So because that change is not constant, this is what makes this function nonlinear. Okay, so it's linear if the rate of change is constant. And the last representation we'll be given is an equation. So we can determine if an equation is a function is if it's linear, if you can write it in the form y equals mx plus b. And if you can write it in that form, then the power is 1 because the exponent of that x is 1. So the degree is 1 if it's linear. For 6, we can write y equals 3.8 as y equals mx plus b by substituting a 0 in front of the x. So this does have a degree of 1. Which makes number 6 linear. Number 7, y equals the square root of x. We can rewrite the square root of x with an exponent of 1/2. So we can rewrite this as x to the 1/2 power, which is the inverse of squaring something, which makes this nonlinear because the degree is not 1. Right, the degree is 1/2. For 6, we can rewrite 6 times x minus 1 as y equals 6x minus 6. So that exponent is 1, which makes it linear. For number 9, x squared minus y equals 0. Well, that degree is 2, which makes it nonlinear. And for 10, same thing. The exponent is x, so the degree is not 1, which makes it nonlinear. Okay, so you can determine if a function is linear or nonlinear from a graph, from a table of values, or from an equation. The next part of 3-2 of linear functions is talking about a solution of a linear equation, and that's just the set of ordered pairs that makes the equation true. For instance, if I had a linear equation y equals 2x minus 1, and if I substitute the value of x equals 5, I plug it in, then I get y equals 9. So that makes 5, 9 a solution to that linear equation. We need both an x value and a y value in this unit for something to be considered a solution. So then a graph of a linear equation includes all possible solutions. So if I were to make a quick little graph, make a line. So any point on this line is considered a solution to that linear equation. Okay, and lastly we have discrete versus a continuous domain. So sometimes the points can be discrete, and other times the points are continuous. Let's start with a discrete domain. A discrete domain includes only certain points, and it usually includes fractions or decimals. Okay, so we're looking for whole numbers. So in this number line, the domain are those specific values. There's just 1, 2, 3, 4, and 5. And that's it. Another way you could represent a discrete domain is with a scatter plot. Okay, that would be an example of a discrete domain. Those specific values are the only solutions. And a discrete domain is typically a variable you can count. One person, two people, three people, one pencil, two pencils, three pencils, because you wouldn't really consider like half a person, 2.5 people. Those values in the domain are whole numbers only. Now, a continuous domain includes all values, including those in between fractions and decimals. So the domain of this number line can be anything less than or equal to 5 and greater than or equal to 5. Okay, including 1/2, 1/4, 1/3, 1.5, 2.5, 3.5, 4.5. Okay, it includes those values in between the values that we see as well. In a coordinate plane, a continuous domain would be a continuous line. And for the variable, it's a variable you can measure. Okay, but most importantly, it can have a part makes a difference. For example, if let's say you grow 1 foot a year. That's a lot, but you don't just grow the 1 foot at the end of the year. You grow throughout. So if you measured yourself at a half of a year, your height would be different. Okay, so you can have 1 year, 2 years, 3 years, but you can also have a 1.5 years, 2.5 years, 3.5 years. You can have those in between values for a continuous domain. Okay, if you eat half a meal, then you've consumed a certain number of calories, versus if you eat a whole meal, then you've consumed a different amount of calories. If you eat half a portion of your required intake of vegetables, that's a possible value of the domain, 1/2. So let's look at some examples and determine, are they discrete or continuous? And then why. Okay, so the input value for number of years, output is the height of a tree. So number of years, because a half a year makes a difference, a half a year is part of the domain, and this is considered continuous. And the number of years can be anything greater than or equal to 0. So for example, 1.5 years is included in the domain. For the second example, we have number of people and how many shoes we have. So number of people, we count those in whole numbers. So that's a discrete domain. Because the number of people must be a whole number. So for example, 1.5 people is not included in the domain. Okay, so if your domain can include fractions or parts, it's continuous. If it's just whole numbers, it's discrete. If the graph just graphs specific values or specific data points, it's discrete. If it's a continuous line, then it's continuous. So let's just go through two examples. One discrete, one continuous. We'll express the function as a table, express it as a graph, and chat about the domain. The linear function y equals 15.95x represents the cost of x tickets for a museum. Each customer can buy a maximum of 4 tickets. So the domain, the possible number of tickets, you can buy 0 tickets, 1 ticket, 2 tickets, 3 tickets, or 4 tickets. That's it. So this domain is considered discrete because you can't buy part of a ticket. It has to be a whole number. So for filling out the table of values, let's start with our domain. Use the function provided and substitute the values for x. These y values are not going to be whole numbers because we're dealing with money, so we'll just do our best to estimate where that point is on the graph. And I'm going to graph each point as we calculate it. So when x equals 0, 1595 times 0 is 0, so we plot the point 0, 0. When x equals 1, so you buy 1 ticket, the total cost is $15.95. So we want to plot the point where x equals 1 and y equals $15.95. You buy 2 tickets. That will cost $31.90. So go when x equals 2, y equals $31.90, just above 30. You buy 3 tickets. It costs you $47.85. So go to x equals 3 and plot the point just below 50. Or you can buy 4 tickets, which will cost $63.80. So go to x equals 4. And the value between 60 and 70. And we're going to leave those points just like that because this is a discrete domain. Okay, we're just going to leave it as a scatter plot. It's just those specific values that are solutions to this function. Can't buy half a ticket, so we wouldn't want to connect the points. Because if we connect the points, then we're saying that any point on that line is a solution, and it's not, so we don't want to make a line. All right, so for 14, a granola bar has 130 calories each. The number of calories C is a function of the number of bars, meaning we define C in terms of B. So calories equals 130 times the number of bars we consume. So based on that, this is a linear function because the degree is 1. But also as the number of bars get eaten, the number of calories consumed will increase at a constant rate. Find the domain of the function. So possible values for b, how many bars could we possibly eat? Well, we can't eat negative bars, but we can eat as many bars as we want. So b can be anything greater than or equal to 0. This domain is continuous because you can eat part of a granola bar. And that part of the granola bar holds some calories, so that will also affect the range. So let's use those same values in the domain. Let's say we want to eat 0 breakfast granola bars, 1 granola bar, 2 granola bars, 3 granola bars, 4 granola bars. And we're going to use the function c equals 130 times b to find out the number of calories consumed. So if we eat 0 granola bars, then we will consume 0 calories. So about the point 0, 0. If we eat 1 granola bar, then we'll consume 130 calories. So when x equals 1, y equals 130. If we eat 2 granola bars, we'll consume 260 calories. So when x equals 2, y equals 260. Estimate right between 200 and 300 for 260. If we were to eat 3 granola bars, 130 times 3 is 390. So go to x equals 3, go up to y equals 390, just below 400. And lastly, let's say we eat 4 granola bars, which would result in 520 calories. So x equals 4, y equals 520. Okay, now in this case, this is a continuous domain. So we can eat a half a bar, 1.5 bars, 2.25 bars. So for this graph, we are going to connect and extend because it's continuous. Now we're not going to continue past 0 because the domain starts at b equals 0. Right? We can't go down here because these are when x values are negative. So we don't want to go down this way. We want to start at 0 and increase to positive infinity granola bars. That's it for the notes on 3-2 on linear functions. After this, you'd want to work on the 3-2 homework assignment.